is widely known in this specialty. And so, well, as I see in the title, the talk will indeed abord several different subjects. And it's a real pleasure, Professor Cohen, to welcome here in this session. So please, according to the rules, I have to cut my microphone and the video also. But people interested in putting questions to the speaker, please use the chat message there in the system. Okay. So
thank you very much, Professor Rebolledo. Thank you very much for chairing this session, and thank you, Paul Ducan, for organizing this session and for leading the Ecodep project and for bringing us all together. I want to talk about Taylor's law of fluctuation scaling. And I'm going to begin with some examples and then move to the theory. This is in case there are any lawyers in the audience. I am using some copyrighted materials under the doctrine of fair use for educational, non-commercial purposes. The sources are always credited. These may not be reprinted or further distributed without permission from the copyright owner. Here is the outline. I will give some examples, then talk about what is Taylor's law, and then give some recent mathematical results and draw some conclusions. I hope to stop in about 38 minutes and then have some questions if you wish. This is a picture of a tornado. It is a tremendously destructive windstorm when it touches the ground. Excuse me. And it can kill people from destroying their homes and buildings. The United States, unfortunately, has more tornadoes than any other country. This is a density map of where the tornadoes are, and there was recently a tornado very near New York City. The outbreaks of tornadoes, when many tornadoes are clustered in time, cause the most damage. An outbreak is defined as 6 or more tornadoes starting less than or equal to 6 hours apart. In recent history, 79% of tornado deaths and most economic losses occurred in outbreaks. And the reason is that the first tornado weakens a building, the second tornado weakens it further, the third, fourth, fifth, and sixth destroy the building and catch people as they're running from the previous tornadoes. Over the last half century, there has been no trend, neither increasing or decreasing, in the number of tornadoes in the United States. There has also been no trend in the number of outbreaks in the United States. What has changed is that more and more of the same number of tornadoes are packaged together into outbreaks. The mean and variance of the number of tornadoes per outbreak and the insured losses have increased significantly in the last half century. The plot A shows the number of tornado outbreaks per year. It is flat over half a century. Plot B shows the number of tornadoes per outbreak. Sorry, my mistake. The number of tornadoes per outbreak increased by 0.66% per year over the half century. The variance of the number of tornadoes per outbreak increased by 2.89%, more than 4 times faster. On the right is a plot of the on logarithmic scale, the mean number of tornadoes per outbreak and the variance of the number of tornadoes per outbreak. And you see a nearly linear relationship with a slope of 4.33. The log of the variance of the number of tornadoes per outbreak rose more than 4 times faster than the log of the mean. This linear relationship is an example of Taylor's law, and my co-author in this work is Michael Tippett at Columbia University in applied math and applied physics. If you look at the distribution in each year over the last half century, the 20th percentile was practically flat. This is called quantile regression. The 40th percentile grew more rapidly, the 60th percentile more rapidly still, and the 80th percentile of the number of tornadoes per outbreak grew still more rapidly. So in terms of percentiles on the horizontal axis over here, the linear growth rate increased. The more extreme parts of the distribution grew faster than the lower parts of the distribution. That is, the tails were spreading out. This is joint work with Michael Tippett and Chiara Lepore, published in Science. That's tornadoes. Let's turn to infectious diseases. This is not my work. This is by Keeling and Grenfell in 1999. Each dot here represents one town or village. And the horizontal axis is the average number of reported cases of measles averaged over all the weeks between 1944 and 1997. The green dots are averaged over this period from 1944 up to about 1966. The vertical axis is the variance of the weekly case reports in the same town. And these are both on log scales. So it's a log-log plot. And you see that there is a linear relationship with slope about 1.7 between the log variance, and log mean of the number of cases per town. That was before there was any vaccination for measles, 0%. During the weeks later on, from the late 1970s until the late 1980s, when 80% of people had been vaccinated, the mean decreased. That's good. You would expect the mean to decrease. People were being vaccinated. The variance decreased. The slope of this linear relationship changed fell from 1.7 to 1.5, but there was still a linear relationship. And after 90% of the people had been vaccinated between roughly 1990 and 97, the slope fell to 1.2, and the mean and the variance decreased. Now, if you had a Poisson distribution, the Poisson distribution has a variance that equals the mean. So the log variance equals the log mean. Therefore, on this kind of a plot, you would expect a line of slope 1 for different Poisson means in different towns. The fact that it's 1.2 tells you that there is some additional source of heterogeneity between towns. That is, this is not a Poisson process for all these different towns. Something else is varying. So this is a beautiful example of the use of Taylor's law, and it's important for planning and for monitoring the performance of the vaccination program. My own work has focused on a disease called Chagas disease, discovered by this man, Carlos Chagas, in 1909. Today, or in 2019, according to the World Health Organization, there are 6 to 7 million cases of Chagas disease, 1 million of them in Brazil, 1 million of them in Argentina, 1 million of them in Mexico. These are countries with the dark blue dots where transmission is active through the insect that transmits the disease. In the United States, there are hundreds of thousands of cases and accidental transmission. The cases come from immigrants. There are cases also in Japan because there are Japanese who have lived in Brazil and then went back to Japan. So there are cases in France, in England, in Spain, all over Europe, East, Middle East, Pacific, originating from this Latin American focus. The vector is this insect here, and it's widespread. Triatoma infestans is the commonest insect that transmits the disease. The parasite is more widespread than the vector because people who get infected travel. The beginning of Chagas disease is a swelling around the eye where the insect has bitten and the infection has begun, called Romagn's sign. The end of Chagas disease is death from a collapse of the muscles of the intestine or heart, occasionally the brain, the esophagus. It's not a good disease, and it kills people in their 30s and 40s when they have families and are most productive economically. My work on this disease has focused with collaborators in Argentina. This is Buenos Aires is down here, and if you travel for about 12 hours north by bumpy roads, you get to this northwestern part of Argentina where there's a lot of Chagas disease. So this is the tip of South America. We zoom into this region and we have a road here and several villages. One of these villages is called Amamá. We're going to zoom into Amamá. You see this hook shape of where the buildings are. If we zoom in, we can see the individual compounds in this aerial photograph here. And now we're going to pick, there's a road that comes down here like this diagonal. We pick one of these buildings, one of these compounds, and we zoom in. Here's that road coming on the diagonal, and this particular compound is right here. And you can see that there are a number of buildings in the compound that's a home. So there's a place where people sleep, there's a kitchen, there's a storage place for goats, there's a storage place for chicken, there's a storage place for grain. This is what it looks like on the ground. There are sticks driven into the ground, and then mud bricks are put between the sticks. In the crack, when the mud dries, the insects have a perfect home. They're very happy living in the cracks in the mud and in the thatched roofs. This is my collaborator, Ricardo Gertler, with whom I have worked for more than 30 years, 32 years now. We've been working on this disease. And the life cycle is the dogs sleep on the floor. 100% of the dogs are infected with this disease. Bugs come and bite the dogs. The bugs become infected. Then the boy goes to sleep, and the bugs crawl up the legs of the bed, bite the boy, and the boy becomes infected. This is a schematic map of a village surrounded by forest, and these are different house compounds. Every house has a domicile where people sleep, a chicken coop, a granary store, an outhouse, a toilet, a goat corral, and a kitchen building. we count the number of bugs in timed measurements in each of these structures. So there are teams of professional investigators who are trained to go and count the bugs. And we get a data array like this. In a village, in the domiciles, the bedroom buildings, this is the bug population per hour of search. 2 men search for half an hour in each building. So the first house had X11 bugs, the second had X21 bugs, the third had X31 bugs. And there's a mean and a variance for these houses. In the chicken coop, let's say there were 5 chicken coops in that village. There's a count of the bugs in each. We calculate the mean and the variance. The goat corral, same. The corn storage building, same. Now, if you plot those means and variances of the different structures on log mean, horizontal axis, log variance, vertical axis, you get Taylor's law, a linear relationship. And this has proved to be very useful because if you have a data point way over here, you go back and check it, what is going on there? And in many cases, we found mistakes. But there's also variability that's real, and that real variability tells you about the control of the populations, whether this is an exceptionally stable population or a highly variable population. In 13 surveys, the slope of these lines was remarkably stable, the intercept stable. So this is one village, Amama. This is another village in Figueira. 3 different species of vectors, Triatoma infestans. This is a different species of bug, and this is a different species. And again, we get Taylor's law. What is the use of this? Well, 1, as I said, is flagging errors. 2 is identifying habits of unusually high or low variability. 3 is designing sequential sampling to reach specified precision, and I'm not going into that. The bottom line is that we convene workshops with the people who live there to give them information about how they can reduce their risk for Chagas disease by plastering up the cracks in the walls of their bedrooms and by keeping dogs out of the sleeping rooms, so to separate the parasite from the human being. And we think that these educational things, based on the research over the last 30 years, has probably saved some lives in Argentina. Okay, now I go to another topic, and considering time, I am going to skip over the detailed explanation. This is joint work with Roland Rau and Christina Bock-Ewald in Germany. And what we did was take age-specific death rates in the United States over the years 1960 to 2009 for each year of age from 0 to 100, calculate the death rate, which is the number of deaths divided by the life years lived, and take the mean over time, or temporal mean, of these death rates and the temporal variance. If you do that, this was Roland's idea. Lo and behold, it's Taylor's law for the United States. And it turns out these are for 12 countries, OECD countries, in the human mortality database with very good data. And you get log-log plots of variance versus mean, a linear relationship. And we have theory for males and females to explain why. Going on to fisheries. This is joint work with Jeppe Kolding, who is a Danish fishery scientist now living in Norway, and Meng Shu, who was a postdoc with me here at Rockefeller and who did the analysis under my supervision. The data for this study come from Lake Kariba, which is the largest human-made reservoir of water in the world. It's made by damming the Zambezi River, which flows between Zambia and Zimbabwe. And our data come from the Lakeside Station right here. Yeppie had access to these data from 1962 to 2001, 40 years of beautifully cared for data. Our publications are in the Canadian Journal of Fisheries and Aquatic Sciences. And if you plot this, each of these boxes is 1 year. So the first one here is 1996, 97, and so on. Let's see, how does this arrange? 1976, 75, starts down here, goes to 76. I see, okay. Bottom, left to right, and then across, and then across. So 2001 is up here, 1962 is down here in the lower left. Each dot is one mesh size. Fishing in the lake for scientific purposes was done with nets of different mesh size. That's the gap in the net. So with a big gap, you catch big fish, and with a small gap, you catch little fish. And for each net size, each mesh size, we took the average and the variance across the whole year at that mesh size. And if you plot those on log mean horizontal axis, log variance vertical axis, the number of fish that you get falls along a Taylor's law line, a linear relationship between the log variance and the log mean. That can be used, and I don't have time to go into the details, to design a stopping line at which the standard deviation of the mean density is a fixed proportion of the mean density. Suppose you collect multiple samples. We want to stop sampling when the mean population density can be estimated with a given fixed precision. And the precision is the standard deviation of mean density divided by the mean density. Taylor's law can be transformed into such a stopping rule. And the data are done in the usual way. And this is an example of a stopping line. And this is cumulative samples versus cumulative individuals. And we applied this to the data for many years. And we found that this method could save work. I should say that this method has been very widely used in agriculture, in soy plantations, in rice plantations, in cotton plantations, to estimate the population density of insect pests with a specified precision so that they could decide whether some kind of insecticide treatment was required. And we adapted that technique to use it in fisheries where it had not been used before. So we found in the Lake Kariba data, using updated stopping lines of fixed precision, like 10%, 0.1, after each new sample, the updated stopping line method required only 21 to 41% of the number of sampling days and 19 to 40% of the number of samples that had been planned under systematic sampling. So this could save a lot of money for in-field work. Last example, prime numbers. Let's take x equal to 10. The primes that do not exceed 10 are 2, 3, 5, and 7. The number of primes not exceeding 10 is 4. 1, 2, 3, 4. The mean of those primes is 4 1/4. You add up those primes and divide by 4. The variance of those number of primes is 3.68. Okay? That's what I'm going to do for different increasing values of x. This plot is x from 0 up to 2 times 10 to the 8th. There are 11 million, roughly, primes less than 2 times 10 to the x equals 2 to the 10 to the 8th. The number of primes goes like that. The mean of those primes goes like that. This is x, and this is the mean of all the primes less than x on log coordinates. The variance of the number of primes less than x on log coordinates is like that. If you plot the variance on log coordinate versus the log mean, you get very close to a straight line. And I have proved that asymptotically, the variance of the number of primes less than x is asymptotic to 1/3 times the mean of the number of primes less than x squared as x goes to infinity. This is published in the American Statistician 2016. Same story with twin primes. These are the plots, and here's Taylor's law for twin primes. The prime number theorem says, discovered and proved by Adamard independently and de la Vallée-Poussin, 1896. If pi of x is the number of primes less than or equal to x, then asymptotically, it's this logarithmic integral lie x or x over log x. If you actually do the plot, you'll find that this logarithmic integral is consistently above the number of primes, and this is consistently below, and it's somewhere in between. Lie x, whoops, okay. So let's use this form of the prime number theorem. Pi of x is asymptotically x over log x. Well, let's create a random variable, capital X, that equals each of the primes less than x with probability 1 over pi x. That's a uniform distribution. The CDF is the number of prime at any fraction r between 0 and 1. The CDF of that random variable is the number of primes less than Rx divided by the number of primes less than or equal to x. That's given by the prime number theorem, pi of Rx over pi of x. That's asymptotic to Rx over log x divided by x divided by log x. Well, if you do the calculation, that converges to R. So that is saying the CDF is of Rx is asymptotic to R. Well, that's the uniform distribution. The same goes if you do the calculation for the Hardy-Littlewood twin prime conjecture. Nobody knows whether the number of twin primes is infinite or not yet, but there is a conjecture that the twin prime counting function is asymptotic to x over log x squared. And again, if that's true, the twin primes are asymptotically uniform on 2 to x. Well, the variance and mean of the primes, if they're asymptotically uniform, the variance is asymptotic to 1/3 mean squared. And the same for Hardy-Littlewood. There's a great generalization of this possible. I haven't published this, but the others are published. The Hardy-Littlewood, Bunyakowski, Schinzel H, and Bateman-Horn conjectures can be summarized in this form, and the same calculation leads to the conclusion that Taylor's law describes the variance and mean of all of these admissible prime configurations with the same parameters, 1/3 coefficient and exponent 2. Okay, I want to tell you that Taylor's law is not magic. It's not always the best model. My colleagues, Robert Poulain and Clément Lagrue, they're two Frenchmen. They work in New Zealand, of course, on lakes in New Zealand. And if you sample parasites from a lake and sample hosts from a lake, animals, you take a net and you sweep animals out of the lake. And then you look inside the animals and see how many parasites do they have. The number of parasites per host, calculate the mean and the variance for different species of hosts. And you plot the log mean and the log variance, you don't get a straight line. That's not the best model. A better model is this quadratic model, which comes from the negative binomial distribution, that the variance equals the mean plus twice the mean squared. That's this solid line here. So there's nothing magic about Taylor's law. It has to be verified if you're talking about an empirical example, or it has to be calculated if you're doing mathematics. Now, in the last 5 minutes or so, I'd like to talk about some recent mathematical results. Here's the data structure, I'll talk about what Taylor's law is in general. You have a set of samples, 1, 2, 3, 4. You have a set of measurements. You calculate the mean and variance in the measurements in each sample, and now you have a set of couples of mean and variance. Taylor, this is Lionel Taylor, who was an entomologist in England. Oops, let's go back. In multiple sets of samples, the variance of population density is proportional to a power of the mean population density. So you can write it this way, or in a linear form by taking logs, or you can take this first equation and divide by the right-hand side. So the variance over the mean to some power equals A. And he was not a statistician or a mathematician, so it's very imprecise in his original publication, and he didn't discover it. This relationship was discovered 20 years earlier by Chester Bliss in 1941, but Taylor's law is named Taylor because he publicized it. Well, variability is fundamental in biology, also in finance, where people have established Taylor's law for stock prices, insurance, for insurance damages. Taylor's law applies in computer science for traffic flows, file sizes, and various other topics, in earth science for hurricanes, earthquakes, rainfall, and various other things. Mathematically, you're given a set of random variables that have means and variances, and you just say that the set is indexed by some label S, and the variance of each random variable is proportional to a power of the mean. In terms of a sample, with sample variance S squared and sample mean M, the variance over the mean to the power B is close to some constant A. Poisson distributions satisfy Taylor's law with slope 1. Different Poisson distributions have a variance equal to the mean, so you get a slope 1. Exponential distribution, the variance is a square of the mean, you get a slope 2. Walled distribution, slope 3. Taylor's law also describes the mean and variance of the Galton-Watson branching process, continuous time linear birth and death process, and many, many more examples. The new mathematical results weaken the assumptions. For example, what happens if your variables have no finite moments? What happens if they're not identically distributed? What happens if they're not independent? And we now can talk about additional measures of variation. The lower and upper semivariance, which is very important in portfolio assessment and management in finance. The local lower and upper semivariance. Also in crop economics, agricultural economics, they use the semivariance for risks to commodity prices, and Sortino-Sharpe Farinelli-Tiboletti ratios, which are widely used indices of portfolio risk. I didn't do the hard part. These other guys did all the brain work. I just came along and made a few suggestions. Mark Brown at Columbia, Victor de la Peña were the first to establish that Taylor's law can hold for sample moments of distributions that have no finite moments. Current collaborations, unpublished work with Mark Brown and Chuan Fa Tong at the University of Texas of Dallas, and Philip Yam at the Chinese University of Hong Kong, with Richard Davis at Columbia and Gennady Samorodnitsky at Cornell. Here are Mark Brown and Victor de la Peña, and they were the first to show. I asked this question when I gave a talk at Columbia in 2014. A couple of years later, they came back with an answer. Amazing work. Thank you, Victor and Mark. So a non-negative random variable is strictly stable if, for these IID variables, you take a sum and it's equal, has the equal in distribution, has the same distribution as, the same distribution rescaled by a power of the number of variables you've added. If X is alpha stable, satisfying this, with alpha between 0 and 1, then X has infinite mean and all higher moments infinite. Every alpha stable law has a Laplace transform, namely the expectation of e to the minus sx, of this form, exponential form. Example, take a standard normal random variable, n with mean 0, variance 1. Square it. Divide, take its reciprocal, multiply by c over 2. That's the distribution of the first passage time in a standard Brownian motion from the origin to an absorbing barrier at the square root of c over 2. If you set c equal to 2, 2 over 2 is 1, square root of that is 1. So it's with c equal to 2, this is the time it takes to move the first passage time from the origin to a barrier at 1. And that is a stable law with alpha equals 1/2. Very easy to simulate in case you want to play with it. And I did want to play with it. So I took a random sample from a stable law with 10 observations, sample size 10. And I calculated the log of the mean and the log of the variance. Then I took a sample of size 100, 10 to the 2, and a sample of size 10 to the 3, 10 to the 4, 10 to the 5, 6, 7, 8, and 9. Notice they don't fall in increasing order because these are random variables with very heavy tails, but they all fall along a straight line. The straight line in this plot has slope 3, and that is calculated in advance. This line is not fitted to these observations. So Mark Brown and Victor de la Peña proved that the slope of the line must asymptotically be 2 minus alpha over 1 minus alpha. Well, if alpha is 1/2, that's 5, what is that? That's 3/2 over 1/2, which is 3. Well, there are a lot more results, but I don't have time to talk about them because my time is up. So I plan to stop talking now. If there are any questions, I would be glad to have them. Thank you for your patience and your attention.
Thank you very much, Professor Cohen, for this very nice talk. Unfortunately, we cannot hear the clap, but that's one of the inconveniences of this system. But well, we have some minute left, say 4 minutes for questions, if there is any question from the audience. Yeah. Victor de la Peña has a question. Do you have any recommendation as to how to I think the sentence is incomplete. Please, Victor. To search for where Taylor's law applies. So, do you have any recommendation as to how to search for where Taylor's law applies?
That's a very good question, an excellent question. The first thing that I look for is a random variable, that a quantity that varies over many orders of magnitude. For example, I would not try to fit Taylor's law to human height, because most people are between 1 and 3 meters in height. Very few people are hundreds of meters high. So don't try with human height, because you won't be able to see any variability sufficient in different samples to have this linear relationship. The second thing I would look for is things where within a given sample there's very high variability. For example, earthquake magnitudes, or rainfall, or, well, lots of things. So you have to look for variability. That would be my answer.
Yeah, thank you. Yes. So just a remark. So for instance, you will not use that with beta distribution, because there, of course.
Correct.
Yeah.
Exactly right. That's the philosophy. That's exactly right. Yes.
Yeah. Yeah. Well, I think there is no other questions. So we thank Professor Cohen again, and we have just 2 minutes left